Welcome back to the class on a power semiconductor drive. In this lecture, we are going to discuss about a static Kramers drive. So this is the circuit diagram for the static Kramers drive. This is a three-phase supply. The three-phase supply is given to the stator winding. The rotor is connected to the diode rectifier circuit, which is converting the slip power into the DC power. The DC power is given to the DC motor. This is the DC link inductance. Both the DC motor and the induction motors are coupled mechanically. This is the field winding of a DC motor. Now we are going to see how exactly this drive will be operating. Whenever you are giving a three-phase supply to stator winding, the flux is created from the stator winding. There is a rate of change of flux linkage with the rotor conductor. There is a voltage will be induced in a rotor conductor. That voltage will be driving a rotor current. Whenever the current carrying conductor places in magnetic field, each conductor experiencing a force, so the rotor will be rotated. There is some amount of slip power is available in the rotor that is converted into the DC power by means of a diode rectifier. That power we are giving to the armature of a DC motor. The voltage across the armature of a DC motor is VD2. VD1 is nothing but a output voltage of this diode rectifier. The armature of a DC motor and the rotor of induction motor both are coupled mechanically. The load torque is equal to the torque developed in an induction motor plus the torque developed in a DC motor. Now, how we are going to change the speed of this static Kramers drive means by changing the field current of a DC motor. Now we are going to see how exactly we are going to get the difference. We know that the average output voltage given by the diode rectifier circuit VD1 equal to 3 root 6 by pi S into V by N, where N is nothing but a turns ratio of induction motor from stator to the rotor. S is nothing but a slip of the induction motor. V is nothing but a the voltage applied to the stator winding of a induction motor. So from this expression, we can say very easily that the VD1 is function of a slip, where slip is a function of a speed. Suppose if the speed of an induction motor 0 at the time of starting, the more amount of voltage is available for the VD1. Because as the speed is increases, suppose the induction motor will be decreases. So here the numerator quantity will be decreases. So the VD1 also will be decreases. Now if you draw the variation of the VD1 with respect to the speed of a induction motor, that will be changing from high value to the 0. So when this voltage is 0 means the speed of induction motor is equal to the synchronous speed. Now one more point here is that the average output voltage across the DC motor, that is VD2 equal to EB plus IRE. If we neglect this armature resistance drop, then VD2 equal to EB. Well, back EMF in a DC motor is highly depending upon the speed. In this drive, the induction motor rotor and the DC motor rotor is coupled mechanically. If the induction motor speed is 0, then the motor speed also will be the 0. The back EMF is 0, so the VD2 is, as the speed of a drive is increases, the back EMF also will be increases. So, if we draw a graph between the EB and N, it will be changing from 0 to the maximum value. Moreover, this back EMF is also function of a field current. Now we are going to see here. On the x-axis we have taken the speed of a drive. On the y-axis we have taken the VD1. At this point the speed is 0. So the VD1 is maximum. As the speed of a induction motor increases, the VD1 will be decreasing. This is the VD2. As the speed of a induction motor is 0, the DC motor speed also will be 0. So 2 equal to EB. So the value of VD2 at 0 speed is 0. As the speed is increases, this VD2 also will be increases at a rated value of the field current. Suppose if the field current is decreases, then the same graph will be shifted downwards. This is the VD2, this is the VD2 at a different values of the field current. The both are intersecting the VD1 A and B. A is nothing but a stable point. B is nothing but a one more stable point at a field current of IF2. Now corresponding speed is nothing but this is the speed corresponding. So corresponding B, this is the speed. So if we change the field current, we can change the speed of a drive between the half of the synchronous speed to the synchronous speed only. Suppose if you want to run the drive below the half of the synchronous speed means that we cannot achieve by changing the field current of a DC motor. Now, how we are going to run the Kramers drive at a low speeds means a diode rectifier circuit should be replaced with a control rectifier circuit. Whenever we are changing this diode rectifier circuit with a control rectifier circuit, this is VD1 at alpha equal to 0. This is the VD1 when alpha is greater than 0. dotted line is representing VD2 at a given value of field current. This is intersecting the point at this point and one more point here. At this point, this is the speed. At the point B, this is the nothing but if we change the VD1 by taking the phase control rectifier circuit, the operating point of a Kramers drive will be less than the half of the synchronous speed. So in this manner, we can increase the speed range of a Kramers drive if you replace the diode rectifier circuit with a control rectifier circuit. Suppose if the Kramers drive is consisting only the diode rectifier circuit, the speed range only limited for the half of the synchronous speed to the synchronous speed only. In this manner, we can change the speed of a Kramers drive. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of my YouTube channel so that I am always available to answer all your questions.